I don't know. It's here. The new computer is here. Somebody has it, and they just have to install some stuff in it and give it to me. Oh, I can't wait. So I think we call this a codomain. This is going from R2 to R2. So just looking at 2 dimensions. Figure shows vectors u, v, and w along with the image that it shows for u and v, but it doesn't show t of w. It says here, copy this figure carefully and draw the image of t of w as accurately as possible. So they gave you choices, but we'll see if we can draw it as accurately as possible. So for this, let's copy this down and make it a little bit bigger. And let's see where TW goes. And what we have to do is we kind of have to find a relationship between U's and V's. And what we're going to do to think about it this way is to remind ourselves that this is a linear transformation and that T of, what is it, alpha U plus beta V, or whatever. Alpha and beta are like the common symbols that they use for scalars, but we can use x1 and x2, I suppose. That's too late. It's already here. Is equal to the scalar times t of u plus the other scalar times t sub v. So the fact that it's a linear transformation tells us that we have this relationship. And so if we can figure out what w is, maybe we can see that w is equal to some linear combination of u and v. If we can figure out that it's a linear combination of u and v, then we can write t of w as the same constants that we use for u and the same constant that we use for v. Whatever those constants are. So what we need to do is we need to take a look at this and say, okay, can we see that this might be a linear combination of them? So what's W look like? V is over here, so if we make a 2V plus U looks like. So if we do, I want to get to, basically I want to get to this point using only V's and U's. So U gets me over here, and then maybe adding V to it will get me here, but I'm not quite there yet, right? So I want to add another V to it.
And a little bit of U, I think, because on mine it looks like W goes a little bit farther in negative Y than U does.
So we could extend it a little bit, but it's not one full extension, so maybe a 1.1 or a 1.2. Okay. So U is going to be multiplied by 1 or 1.1 or 1.2. And then V looks like it's going to be multiplied by 2. So if we imagine making this addition, making this linear combination between U and V, then we're going to get W. Does that make sense? I like to stick with 1, personally.
Well, I mean, here it is on my screen. They don't match up.
Oh yeah, your U is a little short.
Yeah. I was having a hard time. I was just like connecting them.
Yeah.
Like just there. I was like, dude, this is no regular shape. This is some weird.
Well, whatever it is you get. So it's a little bit more than 1. We could put that here, a little bit more than 1 as well. But the idea is that that same number, that same scalar that stretches U will be the same scalar that's going to stretch T of U. And the same scalar that stretch V should be the same scalar that will stretch TV. So now how does that look like? I want t of u to be a little bit more than 1, so I can extend it just a little bit more if I want to, if I need to. But the TV goes down twice as long. So I got this and then another twice as long. So I basically want to add this. Remember, when you're adding two vectors, it's like drawing your parallelogram, and then it's going to be the diagonal. I didn't draw that parallelogram correctly. I could make this look really nice. Could use actual arrows for the vectors.
That already makes a lot more sense now.
Make it all professional looking. All right, so we want an arrow. On it a little bit thicker. Wait, that's not it. What's going on? Oh, here. Damn it. All right. What? What's going on? Damn it, new computer, where are you? All right, so I have the TU and the TV, and I want the TV to be twice as long, and I want the TU to be just a tad bit longer. And then now I want to connect this using a parallelogram. So basically this other vector now, the new vector, no, I need the line. Color, and there you go. So this new vector is going to be my TV vector. So I think all that stuff, I've made this into an arrow, and it should have been a pencil. Or TW. So that's a TW vector that I should be looking for. Okay? And it's all based on this relationship between the input and output values for your linear transformation, how linear combination works. All right? So if I look for the closest one that would mimic that, it's not along the x-axis. It looks like this TW over here is almost as long as TV, but remember, we want to go twice as long for TV. So I think it's this third one. They only give you one check. Final check. All right. So that one was okay. And that had that relationship with linear combinations. All right. Let's go back to, I don't want to do that yet. Let's go back to these different types of things that we could possibly do. And last time where we left off, I think we left off the idea that if you have a linear combination, then if you're, sorry, let me say that again. If you have a linear transformation, can be given by matrix whose columns are the outputs of your basis vectors. And your standard basis vectors, it depends on what they call it E, E sub 1, E2, and they're basically ones in the whatever spot and then zeros everywhere else. So E1 will have a 1 in the one spot, zeros everywhere else. And this can go from 2 dimensions to any higher dimensions that you want. And so so this is really how we want to create our relationships between the transformation function itself and the matrix that we're going to come up with. As long as it's a linear transformation, then it can be written as a matrix. So last time we were working on projecting onto a line, and the day after, Evan showed me his derivation of what that turned out to be. And so I kind of wrote it up a little bit. And so I'm going to have this as a file that you can download if you want, but these are notes that I just kind of took. And this is probably something that you would see I don't know if they have this in the textbook, or you can certainly search this and it will be something similar to this. So if we're going to project onto a line, it would be a linear transformation if the line passes through the origin. That's the only way it's going to be a linear transformation. So a generic line that passes through the origin will be y equals mx. There's no b, because b is equal to 0, right? If it doesn't pass through the origin, then your line does not have a 0 solution, and we can't have that for our transformations, for linear transformations, because remember, t of 0 has to equal to 0 for a linear transformation. So graphically, what this does is that it collapses down to a line, and we saw that we have to find perpendicular lines and find their intersection. And if we would know what happens to the standard basis vector, which is 1, 0, and 0, 1, those are the two standard basis vectors in R2, then we can figure out what happens to the vectors themselves. So let's take a look at what happens with the point 1, 0. And when we did our example, we projected it onto the line y equals 1/2 x. So we can use that as an example to see if we get the same answer. Is corresponding wrong? Corresponding. Next. This isn't a typo, is it? It's half underlined. Where is it? Oh, it's okay. I got these underlines, sorry, bothering me. All right. So for a line, the line has a slope m. The original line has slope m. So the perpendicular has to have the negative reciprocal slope. And then I made up an equation of the line passing through the point 1, 0, because that's what we want to know where that 1, 0 goes to, onto that line. And then I found that the equation of that line is minus 1 over m times x plus 1 over m. And so now I want to find the intersection between this line and the original line, y equals mx. So I set those two equal to each other, and then I got x to equal 1 over m squared plus 1, and then I got y to equal m over m squared plus 1. So 1 over m squared plus 1 and m over m squared plus 1 will be the point that it's going to go to on that line. Okay, so imagine that that's going to be the first column of your matrix transformation. And what did we do? We found out where the first standard basis vector 1, 0 goes to. So 1, 0 goes to this vector, and that's going to be my first column. Now I take my second vector, 0, 1, and I'm going to do the same thing. So the steps are almost the same, and when I was doing this, I just did a lot of copy and pasting. The equation of the line will be a little bit different. Instead of the equation of the first line was minus 1 over mx plus 1 over m, this one it's negative 1 over mx plus 1. And that's from the point 0, 1 projecting onto the line. And so I found the x value again. The x value in this case is m over m squared plus 1, which happens to be the same as the y value from the previous one. And then the y value for this one is m squared over m squared plus 1. So now this is going to be my second column. So putting my first column and my second column and creating my matrix is going to be this. It looks really complicated, but I'm going to see that there's an m squared plus 1 in the denominator for each of those. So why don't I just factor that out, and then I really just have 1 m, m, and m squared as my matrix, and then divide by m squared plus 1. Okay? So you can just trust me, or you can test for yourselves that if you have the line y is equal to 1/2 x, which is what we had last time, and then put the information there, you're going to get that 4/5 business that we got from the previous example. All right? So now beyond this, there's a couple of special cases. There's that horizontal line, the x-axis, and then a vertical line. So let's see what happens to those, because they do talk about that in the book also. So a projection just onto the x-axis means that everything gets wiped out, and then it just goes down directly at a perpendicular. So the line y is equal to 0 times x, or y is equal to 0, is the x-axis. And then if you let m equal to 0 in our scenario, we're going to get 1 divided by 1, 0 divided by 1, and everything else is 0 as well. So a projection onto the x-axis is 1, 0, 0, 0. Now, projecting on the y-axis has our slope to be infinity. Well, a slope of infinity doesn't make much sense, so we have to take limits and stuff. Infinity in the bottom will get closer and closer to 0, right? And if you remember some infinity rules back in Calc 1, if you have the denominator to have a higher power and you let that go off to infinity, this is going to go to infinity faster than the numerator. So that's going to go to 0 as well. When they have the same power, this is essentially going to go to 1. And so m squared divided by m squared plus 1, as m goes off to infinity, is just going to equal to 1. And so this is your other transformation. We can check that. Euler. That's the wrong class. I kind of made the day of. So this is the transformation that we're talking about. And if we make our transformation 1, 0, 0, 0, I should make all the m's equal to 0. If we make the transformations equal to 0, then all these things will just drop to the horizontal line. So let's make another point in this graph over here. Like what?
3, -5.
3,
Well,
-2. So this should drop down to where?
Go to the right one. The arrow.
Well, if this is going to collapse down to the x-axis, where's this going to go? If it collapses down to the x-axis,
3.
3, 0, right? So it should be on this number line. So we should expect the green 3 over there. It's very subtle, but it's there. So there's a point here that used to be down here, but now it came down to just this line 3, 0. Okay. So that's just a quick picture. I don't want to dwell on this too much. I just want to show you that we can generalize our projection onto any line that passes through the origin by this formula, and then there's two special cases where we project onto the x-axis and the y-axis. Okay? So those are a couple of projection problems. All right, and remember the key was to figure out what happens to 1, 0, and 0, 1. So now this would be a good time to go take a look at the problem that Susanna had from 1.9. So this has a shear transformation and a reflection transformation. So we didn't talk about reflections, but we can generalize the idea of reflections the same way we did with the projections. So for a little bit of a shortcut, or more of a shortcut, you can probably look this up in your textbook, and they should have a formula for that. But let's do it. Let's do it by taking a look at what happens to the standard basis vectors. So what we could do is we can, kind of like what we did in the previous problem that we got from the book, we could take a look at what happens to these two vectors. That one should probably be a little longer. All right, a shear transformation that takes E2 into E2 plus 13E1. So remember that E2 is 0, 1, and that gets mapped into 0, 1 plus 13 times 1 and 0 times 13. So it gets mapped into So it gets mapped into 13, comma 1. So 13, comma 1, let's just say it's all the way over here. Oh, I want this in red. And 1 is unchanged. So I'm going to put that there for now. But then there's another transformation that happens, right? And the other transformation that happens is this line. If this is a little too confusing, just pretend that x2 is y and x1 is x. So y equals negative x.
Now, why would you?
Just because this is how we learn to read.
Those are like components, x2, x1 are components on a x vector.
Yeah, they're like your variables.
Okay.
So if it was in 3 dimensions, x, y, z would correspond to x1, x2, x3. All right, so we need to draw this line. y equals negative x, and then imagine the reflection about that line. So let's see what happens to the reflection about this line. Let's do the blue vector first. So we have a 1, 0 point over here. When we are switching the x's and y's like this, the y is going to equal the negative x. So negative x, I think our new vector would be down here, right? Is that correct? So let's call this vector, oh, let's call this is E, E1, and this is going to be T of E1. And that's the big transformation. So what's this point? The 0, negative 1. All right? So that takes care of both transformations because the first part left it alone and then the reflection made it into 0, negative 1. So that's exactly going to be my first column of my matrix transformation. Now let's see what happens to this guy. This guy gets reflected about this graph, and the question is that where is it going to go? Where is it going to end up down here? Let's see what happens. This is the point 13, comma 1, and we're reflecting it, right? So what's this going to be? Negative 13, negative 1. Is that right? So the y is going to be the negative of the x component. So the y, wait. I need this switched, right? Don't I? Negative 13 is the y. So the y is going to be the negative x. Let's try that again. So the y is going to be negative x. So x is 13 in the original. It gets switched over to negative 13 in the y. And then if you solve for the x is going to be negative of the y. So the y is 1. Negative of that is 1, or negative 1. And that's going to be my new x component. So this is how it switched over. And this is going to be your T of E2. So what's going to happen, your matrix A, if you put that together, is simply the columns. 0, negative 1, negative 1, negative 13. Okay? Any questions? I suppose we should check our answer, right? Let's check our answer. We have to do a matrix. Oh, there it goes, matrix. 2 by 2, 0, minus 1, oh, minus 1, minus 13. And we could take a look at how the graphics works for that and how the shearing and the reflection works. Let's do that by looking at this.
Where did your initial values come from? Vectors.
Oh, the E is just standard. So it's the E1 is going to be 1, 0. The E1 is always 1, 0. And then the E2 is 0, 1.
Stated somewhere on the side?
No, but it's not on the assignment, but it's stated in the text.
Trouble?
No, in the text is like part of the discussion.
Oh.
So E is always what we're going to use as standard basis vectors. And in 2 dimensions, there's 2 E's, E1 and E2. and there's these 2 points. In 3 dimensions, there's like the ijk vectors in physics.
Okay.
And so,
Okay.
and in 4 dimensions, then you'll have 4 of these standard basis vectors. Yeah, these are your unit vectors. They're special because they're unit vectors. They're perpendicular to each other, and they're the easy standard basis vectors that we create. Now later on, we're going to see construct an orthonormal that's perpendicular and of unit length. We're going to see if we can reconstruct a different set of standard basis vectors in 2 dimensions, 3 dimensions, etc. All right, so I think I wanted to see if I can take a quick graph of this. I'll take a look at
We have different questions, I think.
square. What?
Or am I going to print a number somewhere? Figure it out.
Oh, it would just be, I guess the only difference would be the 13, right?
Yeah.
What do we want to do? Oh, we want to do a 2-vector x prime y prime equals a matrix times another 2-vector xy. And remember the shear? The shearing vector, I think, is this thing 13? That's a mighty shear. So this is the first shearing, and then the other thing we need to do is we need to switch. And when we switch vectors, we basically made this into a 0, right? What was our matrix again? So 0, -1, and 1, -1, and -13. I guess this is harder to see the actual reflection part. But if you take a look at our original shearing vector in the reflection part and see what happened to the matrix, you'll kind of get some idea of what the reflection matrix might be. Oh, that might be a good problem for you to think about. Oh, it might even be a good exam problem. So if you could just figure out what happens to the standard unit vectors, the E1 and the E2, and then run it through this, you're going to get your column vectors for your matrix that you want. Okay? Any questions? All right, so that was a good question. Now let's talk about one-to-one and onto for these matrices. What do you remember from pre-calculus when you heard one-to-one? So vertical line test would be a function. Horizontal line test. Horizontal line test. Do you guys remember seeing like a bubble thing? Yeah?
For every input output, there's no.
So there's no repeats of inputs. So that's the basic idea.
Every input has a unique output.
Every input has a unique output.
Then trace the output back.
Okay. Do you remember why this was important to study back in pre-calculus or even calculus? the number 1 dash and then another number 1. That's another short way of saying 1 to 1, right? So here's an example of something that's not 1 to 1. When 2 inputs go to the same output, that means it's harder to come back. Another example, not 1 to 1, is y is equal to x squared. Doesn't pass the horizontal line test, right? And then you take two numbers like -2 and +2. They both go to, when you square it, they both get the same answer for periodic functions. Are not 1 to 1. 1.9, yeah. All right. Onto. What does that mean? If something is onto. So this is where the idea of a range is good to distinguish between the idea of a codomain. So onto just means that the range of a function is equal to the codomain. If the range of a function is the same as the codomain, then it's onto. Not onto, example would be y is equal to x squared. So the range, if we define the function f of x as the function that has that takes real numbers and sends it to real numbers, it's going from R to R, right? So all the stuff that we studied are functions that go from R to R. So the codomain of this function is all the real numbers. But we know something special about this. So the range is just the positive numbers, including 0. It can't be negative, right? And so the range is not the same as the codomain. So this is not onto. So whenever there's something missing that you're not hitting with your function in your range, then it's not onto. Yes, sir? We're calling the codomain because it's where the outputs go. The domain is where the inputs come from, and this here is the domain. And then the codomain is where the outputs are, where the outputs live. And in this case, it's going from R to R, so it seems like it's, you know, why make a distinction? But in the stuff that we're doing, we're going from R2 to R4, and so those are different spaces. Yeah.
Where the function take a complex number
Then it's up to you how you define your codomain. If you want your codomain to be just real numbers, then it's just real numbers. But if you define it for complex numbers, then you're missing the whole part of complex parts, and so that's not onto. So it depends on what you define as your codomain.
So what would we say here?
F is not onto.
Is that
No. It's just onto, as in going onto there.
It's just because you had it all caps.
Oh, yeah. No, I just...
So when the range is not the same as the codomain and vice versa, it's
not onto.
So
Yeah.
F was not that.
F maps from R to R. That's how the function works. It's just that your range does not cover everything there.
Because the codomain is, what do you call that? So, what's the values for the codomain?
Codomain would just be any real number, positive and negative. But this function doesn't go negative.
So once the space of the solution to the set.
Say it again?
The space of the solution from the set of the solution.
The space of the solution, the space where the solution is supposed to be, and then the actual solutions themselves are different.
So we don't put like an interval on the codomain from negative infinity to infinity?
Well, we can say that. The codomain is minus infinity to infinity.
Would.
Or you could just say, in this case, just the real numbers would work. And those two things are the same.
And the reason the codomain is negative infinity to infinity because that x squared function can go.
Well, we're just saying that the function goes from real numbers to real numbers. And that's why we just say it goes from minus infinity to positive infinity. Not happy yet, huh?
No.
Okay, we'll keep thinking about it, and then when we start we'll take a look at some of the examples that we have, and then we might see something interesting. Yeah. Okay. All right. Why was this important back in pre-calculus? Why is something that's one-to-one and onto special for us in calculus and pre-calculus? Determines how many solutions there are. Some more.
We needed continuous functions at one point for existing derivative values.
For derivatives to exist. Although I don't know if this would, I don't think this has, this is needed for the derivatives.
I don't know why else we needed it in those.
Yeah, why else? Why else would we need it? What? No. Well, we don't need to know it now yet, but to find the inverse. If it's one-to-one and onto, you're guaranteed an inverse. If it's not one-to-one, if it's not onto, then there's something wrong with your inverse. So your inverse might be, you might need to restrict your domain to have an inverse. And if it's not one-to-one, then there's definitely issues. Like the square root in the x squared function, you know, the parabola is a parabola, but when you take the square root, you only get half of the parabola sideways, for example. The other good examples to look at are the arc sine and arc cosine.
Yeah.
Because you need to restrict the domain for us to make sense out of it. Okay, exponential functions and log functions are examples of things that are not onto, but if you just restrict your domain, then you can have it defined for your domain. So the idea of one-to-one and onto really plays into the inverse, and that's something that we're not going to look at yet, but we will take a look at that a lot later on. But for now, let's take a look at our transformations. And let's take a look at oh, I wanted to do another transformation for you, and I forgot. Rotation. So the rotation transformation is actually given by a nice simple matrix. I just wish I could remember it. Is it cosine and sine? This is negative, and this is positive sign, and then cosine. Trusting you on this. If it's wrong, then we're screwed. So this is the rotation matrix. And it's kind of cool because you can actually see it rotate. And then if we let A equal slider. Let's see if it's actually right. So cosine, oh, that was a minus. So pretty cool, huh? Anyways, so it's a rotation around the origin. And so the question is this one-to-one and is this onto? And the answer is yes, because it's one-to-one. What's one-to-one again? Because if we pick an output, it only will come from one input, right? So if I pick this, if I have a rotation by, what's pi over 2? What is it, 1.57? So 1 point, this is the closest I can get. So that's almost, wait, this is pi. Oh, whatever. So this is a rotation of 180 degrees, almost 180 degrees.
No, that is 90 degrees.
Oh, that's 90 degrees.
Because your axis 7 hasn't gotten all the way, or axis 7 hasn't gotten all the way.
Yeah, I guess pi would be down here. Okay, let's go. This is pi over 2. So if this is my rotation of pi over 2, then if I pick any point in here, like if I pick this corner point in here, that came from one point from a previous, from the input, right? If I pick another random point out here, like 2, 2, that would have come from another random point, but only one point from the domain. Okay, so a rotation matrix is an example of something that's one-to-one and onto. So let's just say that now. So it's a rotation matrix, rotates everything, and you guys can kind of see that it's one-to-one and onto, right? Projection, something that we've talked about already, whether it's projecting onto a line or projecting onto one of the axes. Let's project onto an axis. So the matrix for that is going to be 1, 0, 0, 0. And graphically, we take any random point that we have, and that gets projected down onto the x-axis, right?
So really, we just say it's white.
Its y component just disappears and goes to 0. So now the question is this one-to-one?
Well, it's including on one, but it's not the other one.
Well, it wouldn't be one-to-one, because to show that it's not one-to-one, I need 2 points that go to the same output. So can you give me an example of 2 points that go to the same output?
Something with the constant value, but any
So give me actual 2 points.
1, 1, 2,
1, 1, and 1, 2. So 1, 1, and 1, 2 both go to the same point, 1, 0. Right? So a counter example for something being one-to-one here is that we have 1, 1 goes to 1, 0, and 1, 2 also goes to 1, 0. And 1 over 1 comma 50, 1 comma negative 3, 1 comma anything will all collapse down to 1, 0. That makes it not one-to-one. Okay? Does that make sense, the idea of one-to-one? onto. Is this onto? How would you show that it's not onto? So onto means that I can find something in the output, and then there's going to be a corresponding input for that. Right? So is there something in R2 that's not part of the output? Do you understand my question?
All the y, anything with the y.
Anything with a y component not equal to 0, right? So all the other things with a y value that's not 0, like three, 1. So 3, 1 is in R2, but not in the range. So anything that you can find in the codomain that doesn't get hit by the range, that's not part of the range, if you can find a point, and usually when you can find a point, you can find like an infinite number of points. But if you can find a point that doesn't get hit by the domain, then it's not onto.
So it's not in the range of the transfer.
It's not in the range of the transformation, correct? Okay?
Coming from untransformed in a different range than transformed. No.
Yeah, if it's not in the range, yeah.
Is it possible to have something that's not 1 to 1, but it is onto?
Yeah, but I can't think of one right now.
But it's possible.
Yes, yes. Yeah.
For a case of something where it would be 1 to 1 or onto, where both of the column vectors kind of at least what onto.
Well, I think that's something that we can take a look at in when we deal with matrices. We'll see. And then let's see if, keep that question, and after we introduce a couple of theorems, let's see if that question gets answered. All right, so the reason why we're talking about this is that because of the relationship between the transformation being 1 to 1 and onto has something to do with the matrix, because these are all linear transformations, and we're dealing with matrices. So the big prize for this is to take a look at these two theorems. And I'll just put it together into one page. And we're going general here now. So if we have a linear transformation, then it's 1 to 1 if and only if the Tx equals 0, remember that's a homogeneous system, right? Only has a trivial solution.
Columns are linearly independent.
So columns are linearly independent. Is that what that means? Yeah? And then the next theorem relates to linear transformation with 1 to 1. So if we have a linear transformation and the T maps R onto Rn onto Rm if and only if the columns are the span of Rm, and it's 1 to 1 if and only if the columns are linearly independent. Oh, that's the same thing as the one up on top. So the idea of a span, remember, is that it's a linear combination of all those column vectors. And so that turns out to be the span. Then you're going to cover everything in there. So this was the last thing to be covered in Chapter 1. And I ended up not putting this on the exam because I was going to go over it today. So this won't be on the exam. But I will tell you what's going to be on the exam. So this idea is something that you should probably look over, and then you might have a couple of homework problems that deal with this in 1.9, but we'll definitely revisit this sometime later on. Okay? For other stuff, yeah. Including linear transformations, we're going to continue. I like to continue talking about linear transformations. So, for now though, we have an exam coming up, and instead of that 30 minutes that I thought we might have to review, we only have 10. So, I should tell you what's going to be on the test. Yeah. So your exam will have 5 problems. The first problem, these are the exact headers of each problem. And by problem, I mean this is 5 problems, and each problem will have several sections, A, B, C, or A, B, C, D. The first one would be systems of linear equations. And that's like kind of covers 1.1 and 1.2-ish. Vector equations and span, I think that covers 1.3. 1.4 maybe. So being able to write something as vector in vector equations using vectors would be a good idea to know how to do. Solutions to linear systems is 1.4 and 1.5, I think. Or 1.5, the AX equals B, or AX equals 0. The homogeneous and non-homogeneous system. And then I know this is 1.7, the linear, the spanning and linear independence. So we talked about span already beforehand, but then we reiterated the idea of a span, and we talked about linear independence in 1.7. And then there will be questions on linear transformations. But not one-to-one or onto. So I won't cover one-to-one and onto on this exam. Because all the work that you would do is all the work that you would do in the previous sections anyways. You're going to be checking for linear independence and span, and you'll be checking for solutions and stuff. Yeah? Oh yeah, you get 1 page of notes back and front, and then calculators. So if you guys are, getting used to your calculators and putting in matrices and doing the row reduction, that might be an advantage. It'd be nice to see steps, because if you punch something wrong in your calculator and you get the wrong answer, then I don't know where you made the mistake, then I can't give you partial credit. Yeah, you can use it, double check. And remember that this is 90 points of your test, and then 10 points of your test will be based on homework 1.6, which is not covered, but it's something that you should be able to do on your own. Oh, I think it's the 20th. Yeah, which is the day of the test. Yeah. Wait, did I make it at 11:59 or did I make it before class starts? Let me check.
Are we going to have like a review questions?
I had review questions, but they didn't really match the test. I can post them, but I don't know how much of that would be helpful.
Do you have a recommended where?
My recommendation is just to go over the homework, and then Jake was saying that to go over and review your past homework, you have to go to the Gradebook not in Canvas, but in my math lab Gradebook, and then click on review. That'll open up your homework again, because you can't see it otherwise. I'm sorry, say it again. So it is 1.6 is due at 11:59, but you should do it before you take the test. Actually, it doesn't matter because it's not going to be on the test. So all assignments. I think if you go to course home, one of the selections, there should be a list of things here. One of the selections is the gradebook. If you go to the gradebook, and then you can look at the particular problem, and then you can hit review. Now, if you didn't do it at all, then you can't review it, and you can't open it because it's past. Yosef. Oh, what do you do? Oh, the study plan. It's not. I think it's the same. Yeah, so basically it's just practicing the problems that are similar to homework. So you can go to the study plan. Make sure you go to all chapters because it doesn't show anything here when you click on it first. You go to all chapters and then chapter 1, and then here's a list of the types of questions you can do. All right? So when I see you guys, we'll have a test. See you guys on Wednesday. What? Yeah, so we'll plan to do the whole class time. If you get done early, you can leave. Yeah.
2 questions.